Here in this part, we are going to build up a simple neural network with the help of TensorFlow, a deep learning library, and then train that network with MNIST dataset. So the first of all, we use in TensorFlow, we have another library which is called Keras. So Keras gives us a higher level function which makes us easy to use TensorFlow. So TensorFlow is, you can say, the underlying foundational library, and on top of that we have a Keras which gives us an easy to use interface. And in that Keras we have layers and many different packages, or you can say different functions that can be used for building up neural network. So we get an object of keras.layers in this variable, or you can say, yes, in this object, and then with the help of this layers variable we can build up different layers in a neural network. So all those layers are actually, in neural network, all those layers are fully connected layer. So and all those layers are connected one after the other in a sequential manner. So we first build a model, instantiate a model out of this Keras, which has a sequential ability. So sequential Keras.sequential is used to build up a model which can add all the neural network hidden layers one after the other, or all the neural network layers one after the other in sequential manner. So that's why this one is called sequential. We use sequential here. And so after getting a model object out of this Keras.sequential, we add different layers to this model. So model.add can help us to add different layers. So layers.dense. Dense means that is a fully connected layer. Dense means that every node of a layer is connected to all of the nodes in its next layer. So that's why it is called dense. So you can also find out layers.dense, the functionality of layers.dense. If you want to find out that one, you can simply write help. Yes, if you use keras.layers.dense, then it will give you this function dense and its different parameters or arguments. So you can see the first argument needs to have specifies number of units that you want to have in a neural network layer, and if you want to give any activation function, specify any activation function, then you use activation. And there are different parameters here that you can set on your own. And below you also have a description of that one. So let's move this one for the time being. So coming to here, building up of a neural network. So here you can add up a layer.dense. So it will construct a layer for you. So 32 means the number of units or the number of neurons you want to have in a layer. And since this one is the first layer, because we are building up layers sequentially, one after the other, so we need to specify in this first dense layer the number of inputs. So since our image size is, each image size is 28 times 28, so you can specify it here that how many input nodes you need to have. So 28 times 28, that is around 784. And if you want to specify the activation function in your first layer, then you can specify here sigmoid or ReLU or any other function, activation function here. Then you move on to next layer. You add another layer, layers.dense, with 64 nodes and activations you're specifying here is ReLU. Then you have another layer. Then you have a final layer or output layer. So since you have to classify digits, 10 digits starting from 0 to 9, So it need to have, we have 10 classes, so the output layer that need to have 10 output nodes. So that's why we are specifying here 10, and we are using activation function softmax that is used for multi-class classification. So you run it, and after that, if you want to see the summary of that model, so you can run model.summary. So it will give you the number of nodes in each layer and the and total number of parameters that need to be trained. After that, the next step is you compile that model. So model.compile, and during this compilation you need to give it optimizer, any appropriate optimizer like ADAM or ADAGRAD or RMSProp, and you need to specify the loss function or your objective function. So here we have studied either scared loss function or entropy loss function. So we are using entropy loss here. So sparse categorical entropy loss cross entropy means that since we are not encoding our labels one hot encoding, so that's why we are using the sparse categorical cross entropy. And you also define metrics that you want to measure the accuracy. So you run it, it will compile, and now the next step is to train your model. And for model training we use this one function is model.fit. So model.fit is used for training our model. So model.fit, we supply our training data and its labels while to train our model. So, but before that, we need to see that what are the dimensions of our training data. So do our training data, the dimension of each training image, is that compatible with our input dimension, the number of inputs or input dimension of our neural networks? So there should be a compatibility between our input dimension for a neural network and the size of input image or the size of input that we are going to supply. So if we look at here, for the time being, at the moment, if we see the size of each training data, so that is 60,000 times 28 times 28. So that is the dimension of our training data. But as you have seen, while building our neural network first layer, so the input layer has dimension of 784, 28 times 28. So we also need to make our training data compatible with that dimension. So if you look at any one example here, so it has size 28 times 28. We don't need that. We need 784. So what we do here, we reshape our training data. So xtrain.reshape, and we say that the first dimension should be 60,000 and second dimension of our variable should be 28 times 28, which is 784. So, and in the same way, we change the dimensions of our test data. So when we run it, and now if we see our training data, so its dimension is now 784. Or if you look at the whole training data, so that is 60,000 samples, and each sample is of size 784. So now we supply this type of data. Now we have changed the dimension or make it compatible with our input layer. So we supply that training data with its labels, and we can supply number of epochs, and we can also supply it a validation data. So for the time being, we are using test data as a validation data, and we can also set this verbose value. We can set it to 0 or 1 or 2. So if verbose is equal to 0, so while training our model, it will not give us any output, so it will not show any progress in our training. However, if we change it to 1 or 2, it will give us it will tell us the progress of our training. So now if we run this one, we are using only 10 number of epochs, but you can increase it because 10 number of epochs are not sufficient. So run it, and now it is telling us, because of the verbose equal to 1, that it is giving us this information, giving us the progress of our training for each epoch. So now we have trained our model with 10 epochs, and while training it used batch gradient descent because we didn't use any mini batches. So if you want to train your model using mini batches, then you can try this one. You only have to add this new parameter here. Batch size is equal to, it can be 128, 256, 512, whatever you like. The value should be 2 raised to the power some value, and then you can see that the whole training will run more quickly. So you can try this one on your own. Okay, so after training our model, we have stored all the values or all the information about our training in this variable history. So we can use history further to find out different information, like if we want to see the accuracy at different iterations, that can be found in history variable. If we want to see the validation loss, that can also be found in this history variable, validation accuracy. So down here we are using that history variable, so history.history loss. So it will give us training loss, history.history validation loss. So it will give us validation loss, and we want to plot them together. So since we have trained our model without using any mini batch values, so it means we trained it with the help of batch gradient descent. And here we are specifying the number of here specifying the y limit. We are setting the range of our y-axis, and legend means that since we are plotting only two values, training loss and validation loss, so we have to label them here. So we use, for that purpose, we use this legend. So if we run that one, what we can see, so this is giving us, one is the training loss and the other one is validation loss. So if you run your model, train your model for more number of epochs or iteration, then you can plot those values, those two curves, for longer number of epochs. And you can also access different values with the help of this variable, history.history. Now you can try different variations, and you can learn on your own that what are the effects of those variations. So here I have listed some variations you can try.